Hello and welcome back to Physics 151 Online. Today we're going to work out a formal derivation that will explain the relationship between torque and a new quantity that we will call angular momentum. And we'll see that this relationship is very similar to the relationship between force and linear momentum p. So let's start by going back to Newton's second law in the form where the sum of all of the forces acting on an object is equal to its mass times its acceleration. And to keep the notation simpler, we'll replace the summation with just a capital F vector, realizing that this represents the net force on the object. Okay, so since acceleration is dv dt, and then we can group the m inside that derivative, we remember that the net force on an object can be written as the time derivative of the momentum vector. And this is our starting point. So now, let's use the definition of the torque vector on an object, remembering torque is equal to r cross F, employing the vector cross product. So force can be replaced with dp dt. So the net torque on an object is equal to r, this r vector, crossed into the time derivative of momentum. Now there's a distributive law for cross products, and this is the part of the derivation where we kind of have to know where we're going in order to use this next relationship to get there. But you'll see how it works out in just a second. So if we take the time derivative of a vector cross product, r cross p, then there's a distributive law where the first term is dr dt crossed into vector p, and then r crossed into dp dt. And that kind of makes sense by looking at the expression that we started with. Now why are we using this? Well, because if you look at the second term on the right hand side, that's exactly what we found the net torque on an object is equal to. Alright, so in the next step we will see that the net torque, which is r cross dp dt, using this equation here, r cross dp dt is equal to what's on the left hand side minus the first term that's on the right hand side. Alright, so tau, which is r cross dp dt, is equal to d by dt of r cross p minus this term dr dt cross p. And it's not obvious exactly how this is going to help us until we look at this last term on the right hand side. And remember that dr dt is the same as the velocity vector. Okay, now velocity crossed into momentum, v cross p, well that's the same as v cross mv. And one of the things that we've seen using the vector cross product is that any vector crossed into itself, or anything parallel to it, is equal to 0 because the angle between the two vectors is 0, and the sine of 0 is 0. So this dr dt cross p term drops out completely, and that leaves us with the result that the net torque on an object is the time derivative of this vector cross product r cross p. So it's got linear momentum in it, but we have the vector r crossed into that. Alright, and so this suggests that we might want to give this term in parentheses some kind of name, because it's the time derivative of that quantity that's equal to the net torque. And in rotational motion, we define this quantity to be the angular momentum, and we use capital vector L to denote the angular momentum of the object. So it's an object that has a certain linear momentum, or at least parts of it do, and then with respect to a particular axis, the r vector tells us where that object is with respect to the axis. So L is the linear momentum, is the angular momentum. Now, once we make that definition, we can rewrite what is essentially Newton's second law for rotational motion as the net torque is equal to the time derivative of this angular momentum vector. And remember that this is very similar to the place that we started on the last slide, which was to say that the net force is equal to the time derivative of linear or translational momentum. So we have a version of Newton's second law for linear motion, and then we have a version of it for rotational motion, and they're expressing similar relationships but for slightly different quantities. And this angular momentum definition will give us a new physical law that we'll get to in just a minute. Alright, now we have basically filled out completely this table that shows us the relationship between various quantities that describe translational or linear motion, and then the corresponding quantities for rotational motion. And you'll see that the last two that we've done in just the last couple of days, we've talked about how force has a rotational counterpart that we call torque, and the torque depends on not only the direction of the force, but where the force is applied, which is what the r vector tells us. And then linear momentum has a counterpart of angular momentum. And again, not only does that depend on the linear momentum of a part of a rotating object, but where that part happens to be relative to the axis. And notice that if we're just concerned with the magnitudes of these two quantities, that we can often write the tau, the torque magnitude, as F times r perpendicular. And in the same way, we can write the magnitude of angular momentum as P, linear momentum, times r perpendicular. And that r perpendicular depends on where the axis is located. And as I've mentioned several times in class, I hope that thinking about these rotational quantities like this will assist you in remembering the definitions of those quantities and where they fit into various equations for rotational dynamics. Now, this reminds us that we can go back to Newton's second law, and the way that we developed the law of conservation of momentum was to look at Newton's second law and ask what happens to a system when there's no net external force acting on it. So here's what you hopefully will remember. If we have a net force, which is time derivative of momentum, and if that net force is zero for an object or for a system of objects, then that means the momentum of that system is a constant, right? Because the time derivative is zero. It doesn't change with time. And whenever we find these quantities that under certain conditions are constant, that gives us the basis for a conservation law. And so for rotational dynamics, we have something very similar. The torque acting on an object is equal to its time derivative of angular momentum, and if that's equal to zero, there's no net external torque, then for that system, the net angular momentum is a constant. And this gives us the basis for the law of conservation of angular momentum. The way that we will employ this in analyzing the results of collisions and other kinds of interactions between objects that can rotate is often to say that the sum of all of the initial angular momentum components is equal to the sum of all of the final angular momentum terms for a system. So let's look at what basically is a collision between two objects where one of the objects at least is able to rotate around a fixed axis. And let's ask ourselves, what kinds of conservation laws can we use to analyze this collision? So a ball with a mass m and initial velocity v0 is going to collide and stick to the end of a rod that hangs vertically and can rotate about a fixed axis that runs through the top point of the rod. Alright, so the ball sticks to the bottom of the rod, and we want to know, right after that collision happens, and then they begin to rotate together, what is the angular velocity of the system. Now, of course, if we wait long enough, this whole system will swing upward around the rotation axis and will eventually come to a stop and then swing back down again. But we want to know, right after the collision, what is the omega, or the angular velocity of the system. So in order to think about the three conservation laws that we've developed for use in various situations, we have to think about the conditions for those so that we know which ones we can use. So is mechanical energy conserved? Is the sum of all of the kinetic and potential energies of the system the same before and after the collision? And we should easily be able to say no, because the two objects stick together. And whenever two objects stick together, some energy is lost. Some kinetic energy is lost in the deformation that happens. And so this collision is inelastic. We cannot assume that the kinetic energy is the same before and after. What about linear momentum? Remember that the condition for linear momentum to be conserved is that the system can experience no net external forces. So what's the system? The system is the hanging rod and the mass, m. So when they collide, then they begin to move. We have to ask, is there a net force on that system? And it turns out that there is. And the reason that there is, now in the initial picture, when the rod is simply hanging vertically and the collision hasn't happened yet, there is no net external force on the rod because gravity pulls it down and because the hinge force pulls it up. And so it's not accelerating, so there's no net force. But immediately after the collision, when the system begins to rotate, there must be a net force because any object in circular motion has to experience a net force acting towards the center of that rotational motion. And so after the collision, when the rotation begins, now all of a sudden there is a net force. And so linear momentum is not conserved. We can't write down some conservation of linear momentum expression. What about angular momentum? The condition for angular momentum to be conserved is that the net torque is equal to 0. And we should be able to see that when this collision happens and immediately afterward, any force that's acting on that system is in the vertical direction. So gravitation supplies a force downward, the hinge provides a force upward on the rod, and both of those forces pass through the rotation axis immediately after the collision. And so they do not give a net torque. Even though there is a net force, the net force passes through the axis. And so there's no net torque, and angular momentum is conserved. And as a result, we have discovered now the tool that will allow us to analyze this collision and answer the question, how fast the rotational velocity is immediately after the collision. And so what we need to do now is figure out a way to calculate the angular momentum of that rod. So if we go back to the picture for just a minute, immediately after the collision it begins to rotate, right? But it's not obvious how we apply the expression for angular momentum of a point particle, because the rod is composed of lots of individual point particles that stretch from the rotation axis all the way down to its end. So how are we going to find the angular momentum of the rod? And there's a very simple expression for that. We'll return to this arbitrary shaped object. It's rotating about an axis that passes through the origin. And we'll look at one mass piece of that object at a distance r away from the axis. So remember, we said if we are only concerned about the magnitude, we can write the angular momentum, magnitude of the angular momentum of that piece as just r perpendicular times p. Well, p will be delta m times v, and the perpendicular distance, because that object is in circular motion around the axis, is simply r. So we have r initial, r sub I times p sub I, and p is delta mv. So that gives us the contribution of that one little piece to the overall angular momentum of the object. Now, let's substitute v is equal to r omega, and then sum up the contribution to the angular momentum from all of the pieces of the object. So L sub I is now r sub I squared times delta m times omega, right? And we add up the contribution of all those pieces. We can simplify this because omega is the same for every point on the object. If it's a rigid object, omega comes outside the summation, and lo and behold, look at this summation. We have seen this before. It's nothing more than the sum of the mass times the distance squared from the axis. And that's the moment of inertia. So what we see for this expression is that the overall magnitude of the angular momentum of a rigid object when it's rotating around a fixed axis is simply equal to the moment of inertia times the rotational velocity. And look at the analogy. This is something that we can remember from the corresponding quantity for linear momentum. Linear momentum p is mass times velocity. Angular momentum L, if we replace mass with moment of inertia and v with omega, we get the correct quantity. And notice, even though in the derivation above we were just adding together the magnitudes of the L of each piece because they all have the same direction, in general we should write this relationship as a vector equation, remembering the definition using the right-hand rule for the direction of omega and therefore the direction of L. In the sketch on this slide, since the rotation is in the counterclockwise direction. If I take the fingers of my right hand and curl them in that direction, my thumb points out of the board or out of the slide, and that is the direction of omega, and it also turns out then to be the direction of L. Right? So using the right hand rule, we can quantify the angular momentum as a vector and not just its magnitude. So with this in place, we can now return to the example problem and figure out the answer to the question, what happens after the collision? Because now we have a way of writing down the angular momentum of that rod after the collision happens and it begins to rotate with a rotational velocity omega. And we'll finish that problem in class.